Okay, so finally we are now going to start a new section. Here we are going to study the two fundamental theorems of calculus. And today we are going to see the first fundamental theorem. Let's see the statement first. Here we have two real numbers a and b, where a is less than b. And there is a Riemann integrable function f from the closed interval a comma b into R, of course, because we are only considering real valued functions. Now, with the help of this function f, we define another function capital F, which at any point x, and by the way, capital F also has this same interval as its domain as small f has. And the definition of capital F is given by this integral. It's the integral of small f in the interval from a to x, and x is that chosen input and x is coming from here. The claim then is that this new function is continuous on this interval. Additionally, if the original function small f is continuous at some point x naught, then capital F is differentiable at that point, and the derivative of capital F at x naught is equal to the value of the small f function at x naught. This is the first fundamental theorem of calculus. It relates the derivative of that second function with the original function. Originally, the second function f is in a sense the integral of the first function. So the first function is in a sense the derivative of the second function. So these are opposite. So now we are going to prove this. And before we do anything in the proof, we have to first of all make sure that this capital F makes sense. Simply considering this integral, is it okay? That is what we first have to see. We are given that small f is Riemann integrable. So we know that small f is integrable over the closed interval a comma b. But if we make the interval smaller by choosing some x from here, over this subinterval also is f integrable. Yes, it is. But what is the justification? So with that we are going to start. That justification comes from the properties of Riemann integral. You may remember that the last property of Riemann integration tells us this. We have this function, right? We have already encountered a list of basic properties of Riemann integrals. I am talking about those properties. The last on that list is this. Say you have your x here somewhere. Then the last property tells us that the integral of f over the entire interval is equal to the integral of f over this plus the integral of f over the other half. Other half means the other part. And it is that thing where actually, truly speaking, if we are calling this interval I, this one j and this one k, then truly speaking, we should consider the restrictions of f to j and k respectively. This notation may help you remember what we are talking about. So this property not only tells us that this equation is true, but in that also is included the fact that these integrals themselves exist. In particular, this integral exists, which is what we see here. So yes, for every x coming from this interval, you get a unique real number. So capital F is a well-defined function. Now we are going to first of all show that capital F is continuous, and then we go for the second part. Okay, so let's now start the proof. We will need this property again in the proof also. So the proof starts like this. Note that we are not saying anything about continuity of small f in general on its domain a comma b. Small f is just integrable, and by now we know very well that an integrable function need not be continuous. However, small f needs to be bounded because integrability has been defined only for bounded functions, and that's what we start with. Since small f is Riemann integrable, it's bounded. So there exists a positive real number n such that minus n is less than or equal to f of x, which is less than or equal to m for all x belonging to our interval. Alright. So now next what we do, we are going to choose 2 points in this interval which are distinct, say x and y, and we calculate the difference of the capital F values of x and y, and let's see what we get. Now let x and y belong to a comma b such that x is less than y. Then f of y minus f of x. We first we apply the definition of this function. This is the integral of small f over the interval a comma y minus the integral of small f over a comma x, and it turns out to be equal to the integral of small f over x comma y. But how? And that is that property with which we started the discussion, and it is Theorem 1141 part H, that last property, by H. But exactly how? Let us take a moment to see exactly how we are getting this. It's not very difficult. You see, what is the relationship among these real numbers a, x and y? The relationship is this: a is less than or equal to x and x is less than y. So by that property, the integral of f over a comma y is equal to the integral of f over a comma x plus the integral of f over x comma y. So that is why this minus this is equal to this. If you are keenly observing, you may have a confusion. The confusion is that these two intervals do not exactly form a partition of this. Ideally, I should have written open interval here. But then what gives me the liberty to write closed interval here? There should be an answer, right? And the answer is that, say, actually, if you apply this theorem, part H, you will get open interval. Now, if you are considering closed interval, that means you are considering one extra point. And if I really be careful about that, because we are discussing about this in detail, so let me just show it fully, because why not? We are really getting only this, but then we note that this actually equals this plus this, and you convince yourself that this is 0. Why? Because this is a degenerate interval. You apply the definition of Riemann integral over a degenerate interval, you will see that you get 0. You apply the definition itself. You take majorizing functions, minorizing functions, their integrals. You apply that definition, you will see that you get 0 here. The original function can be any function. And that is why this equals this. So we can consider closed interval here. Geometrically, this corresponds to, if f really is a non-negative function, then you know very well that the integral gives you the area under the graph of f above the x-axis and between these two vertical lines x and y. This is the link between the numerical integral and the geometric area of that region. What this corresponds to is the area above the point x, below the graph. That means the area of that line segment, which is 0. A line segment has length, but its area is 0. That is why this is, from that point of view also, this is 0. So that's how we get this. Okay. So what do we do next with this thing now? Now next we apply the fact that f is bounded above by capital M and below by minus capital M. Now, so their integrals will also be related like that. For example, the integral of f that you see here will be less than or equal to the integral of capital M over that same interval. And here we are again applying another basic property of Riemann integrals, which is part E of that same theorem. So we write now by theorem 1141E. This is less than or equal to the integral of m over x comma y by another property which tells us what the integral of a constant function is. This equals m times the length of this interval, that is y minus x, and similarly this is greater than or equal to the integral of minus m over that interval, which will be minus m times the length. However, we just now calculated that this integral is capital F of y minus capital F of x. That is minus m times y minus x is less than or equal to f of y minus f of x, which is less than or equal to m times y minus x, or keeping in mind that y minus x is positive, we get this. Less than or equal to m times absolute value of y minus x. Okay. Note that this inequality is also true if x is equal to y. X is actually not equal to y because we chose x to be less than y, but if they were equal, then this side would be 0 and this side would also be 0. After all, because there is a possibility for equality, so this general inequality in that case is also true. If, however, y is less than x, then we similarly have this. So that was y minus x, this is x minus y. Or, but you can of course write fy minus fx here and y minus x there because there is absolute value function. So we have this. We have this inequality for any 2 points x and y coming from our interval a comma b, regardless of which one is greater, which one is smaller. They can in fact be equal also. Or same thing, we have these inequalities. We are again writing these because, because it is in this form that we are going to use them now. Okay. Now what do we do? We are now going to consider any point in our interval and we will call it, say, x. We can give it some other name also, but the author has decided to write it as x. And we are also going to choose a sequence of points in this interval that converges to x. Now, let x be a point in our interval and let x then be a sequence in this interval converging to x. You understand why we are considering these things, because we want to prove that capital F is continuous at this x, and we want to do so sequentially using sequences. So you may remember that sequential formulation of continuity of functions. That thing we are going to do here in converging to x. Alright. Now, if any 2 points come from our interval, we have these inequalities. In particular, we also have this. For each natural number n minus m times xn minus x less than or equal to f of xn minus f of x less than or equal to m times the absolute value of xn minus x. Because after all, x as well as all the terms of this sequence are coming from a comma b. That's why these inequalities are applicable. Since xn converges to x, so this is something we have. Which is just a simple fact. And that is why this sequence approaches 0 as n approaches infinity, and so does this sequence. So by the squeeze test, the middle terms also converge to 0. Hence, by the squeeze test, that is f of xn minus f of x converges to 0, which by the limit laws further implies that f of xn converges to f of x. So what have we shown? We have shown that any sequence, x of course is our chosen point. So for any sequence xn in our interval that converges to x, f of xn converges to f of x. So by the sequential formulation of continuity, f is continuous at x. Thus, not small f, capital F is continuous at x. But x was any point in the closed interval a comma b, so f is continuous on the entire interval. Since x is arbitrary f is continuous on economy. So we have proved one half of the claim. Now we go for the second half. Let x naught belong to a comma b and small f be continuous at x naught. Choose a positive epsilon. That because of continuity we are going to get a delta. There exists a positive delta such that the distance between f of x and f of x naught is at most epsilon whenever our x comes from the closed interval but also in the delta neighborhood of x naught. And we give this intersection a name also. We call it I. So this is a comma b and the delta neighborhood of x naught is x naught minus delta comma x naught plus delta. What is our aim now? We want to prove that capital F is differentiable at x naught and its derivative at x naught is small f of x naught. And in trying to do so, we are going to use a previous result which has the name Newton's approximation. If you remember, when studying derivatives, we came across this and we proved it. So this is our aim now. Now, we want to show that this inequality mod f of y minus f of x naught minus small f of x naught times y minus x naught less than or equal to epsilon times mod y minus x naught for all y belonging to I. You may remember this inequality. It is Newton's approximation. It comes from that statement. And that statement is proposition 10(1)(7). Because then by proposition 10(1)(7) it will follow that this is differentiable at x naught and this is the derivative. So now our main aim is to first of all establish this for all y belonging to I. So let's now fix y. Oh, and one more thing, before we do anything, Let us note that this inequality is true for one particular value of y. It just simply is true, which is when y is equal to x naught. If y is equal to x naught, what do you get? F of x naught minus f of x naught, so this becomes 0. This term also becomes 0, this one also becomes 0. So in that case the inequality is trivially true. Note that let us give it some kind of name also. Let me call it star. Note that star is true when y is equal to x naught. Let y be some point in I such that y is greater than x naught. There is that other case where y is less than x naught. That case is exactly similar to this one. So that in the book also it's not done. I have done this and I will just leave it to you. Okay. Now f of y minus f of x naught will be what? We have already done one calculation like this. So this will simply be this integral. All right. Okay. Now let us go back to the beginning of this second part, where we had that those inequalities involving the small f values and small f value at x naught, where you have epsilon, delta, that thing. We have the distance between f of x and f of x naught is less than or equal to epsilon. In place of that, we can also write these inequalities. F of x naught minus epsilon is less than or equal to f of x, which is less than or equal to f of x naught plus epsilon for all x belonging to I. Now note that we have two already chosen points, small y and x naught. Since x naught and y both belong to I and I is connected, the reason for I to be connected is that I is the intersection of two closed intervals and they have an intersection, a common point, which is x naught. And because of that, the intersection is connected, it's not a disconnected set. And when you have such a connected intersection of two closed intervals, then the intersection itself is an interval. And because it is an interval and because it is connected, so do you remember the definition of a connected set on the real line? Whenever you have a connected set, say this is a connected set, the line segment between these 2 points, geometrically I am saying, you take any 2 points in that connected set, everything that lies between those 2 points also lies inside the set, inside this entire set. Similarly, now anything that lies between x naught and y is going to lie inside I. Or in other words, the closed interval x naught comma y is a subset of I. This is not true when the set is disconnected. For example, let me just give you an example of that as well. Say, you consider the union of these 2 closed intervals. This is not a connected set. And as a result, if I choose 2 points, say 1.5 and 3.5, both these points are in the union, but not everything that lies between them is in the union. For example, this point, although it lies between 1.5 and 3.5, fails to be inside the set because it's neither here nor here. So there is a disconnection, and that's why that property fails. But now we have that property. Okay, so because it is connected, this is a subset of I, which means that any real number we choose from this interval, for that real number as well, because it will belong to I, these inequalities are going to be true. Hence, in fact, let's just write that first. Or this is how let me write it. Hence, for all x belonging to x naught comma y, now what we do, we will integrate over this interval all the terms. And what gives us the justification for doing that? It is that property, Theorem 1141 part E, okay, which lets us have inequalities between integrals. So this is what we are going to get if we take integral over x naught comma y of all these things. F of x naught minus epsilon less than or equal to integral of f which is note that this and this are constants. They do not change as x changes over this interval. And that is why we can calculate these integrals. This will be the constant times the length of the interval, y minus x naught. And what is this middle integral? Just now we calculated that this is f of y minus f of x naught. And this is less than or equal to this other constant times the length of the interval. Or, so let us now just do the multiplication. That will make things a little more clear. Minus epsilon times y minus x naught, which is less than or equal to f of x naught plus epsilon, I am doing multiplication, times y minus x naught plus epsilon times y minus x naught. Next, what we do, we will continue. If you want, you can also write implies instead of writing ors. We can subtract this quantity from the three terms. That will give us these inequalities. minus epsilon times y minus x naught. Note one more thing, that since according to how we have chosen these things, y is greater than x naught. So this is positive. That means I can also write absolute value. This is less than or equal to, we already have this, but now minus of this, which is less than or equal to or now we are almost there. This is what we have to show, right? And the other case is similar, in which y is less than x naught. Okay, so I urge you to go through that. So once you complete that, that means we have shown this. Oh, and one more thing, do not forget that where is our delta? Delta is there inside the interval I. Okay, and do not forget that this y we have chosen from I. Y is any point in I. So that's just it. That's the proof. And we can, of course, we have to conclude. Hence, capital F is differentiable at x naught, and by Newton's approximation, its derivative at x naught is equal to the value of the function at x naught. This result may not exactly be something that you may remember from your school calculus course, because we do not normally encounter this. But the second fundamental theorem is what we use all the time when integrating something. We first find the antiderivative of the integrand and then put the upper limit minus the lower limit, that technique. Okay, the second fundamental theorem states why that is true, I mean in what sense that is true, and then proves it. We will do this in the next calculus, real analysis video. That means this coming Sunday. And tomorrow is Monday, right? So tomorrow we again go back to what I forgot the schedule. What do we do on Mondays normally? Oh, number theory. Yes. Okay, so we will see that tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.